Testing, testing. Okay. Before we get started for today's things, do you have any questions about the exam for me? So what you have right now is only your free response. I have your free response written down, and then I'm gonna take and drop off. I'm paying for waiting because now it's the hottest freaking day of the week. I'm gonna take and drop off your multiple choice, and I'll get those grades in before the day is out. I'll also post a video solution before the day is out. I am going to do a YouTube live, I'm assuming Saturday evening, which is like such a lame time, but I'm doing a bunch of other stuff this weekend, so that's like my only time. And then the other thing I was gonna say is, oh, I noticed a lot of you, and this is relevant because chair structures are still coming up. Like maybe even on your quiz today, chair structures might still come up. Or not quiz today, but quiz that's due virtually by tomorrow. So I want to make sure you know how to draw a chair structure. So if you go to my YouTube video, there's a playlist and it's called Topical Reviews. And there is one that says, I think it's called How to Draw a Chair. Where is it? How to draw cyclohexane and chair conformation. And the thing is, there's like a very specific way that you're supposed to draw these lines up and down so that you can actually tell, no matter who's drawing it, what's going to be axial and what's going to be equatorial. So go through on this video how to do that. But there were some of you who drew your axial and equatorial. It'd be like you would draw it like exactly halfway between the conventional standard for where axial and equatorial is on your exam. And I was like, so is this axial or equatorial? I don't know. Or you would draw like two pointing up right next to each other. And I'm like, well, the one of these should be equatorial because two pointing up alternate axial, equatorial. So if I commented about working on your chair structures, which I think there's probably like 10 people, maybe more. So that's like close to a quarter of the class. I want you to go back and watch this and practice drawing your chair structure in the convention before you take your quiz or do anything else. And then just to give a visual of that so that you can see that there is one convention, it literally mimics the axial equatorial. And so I'm going to show you the different ways the arrow should point. So this is your basic chair, and I draw my chair as kind of like a weird sideways Z, and then I come down and then go over and then make these two meet. That's how I draw my chair. Okay, and then I'm going to draw all the ones that are pointing up, and the ones that point up alternate. So axial, up equatorial, up axial, up equatorial, up axial, up equatorial. So if you drew something two together that were up and both axial, that would be wrong on like a lot of different levels. One, because it was a 1-3 question, but two, because you can't have two up right next to each other that are both axial. Okay, and then for all the ones that are pointing down, there's also the convention. If up is axial, then down has to be equatorial. Up is equatorial, so down has to be axial. Up is axial, down equatorial, up is equatorial, down is axial. Equatorial, axial. So see how if you are just drawing the down ones, they're alternating axial, equatorial, same thing with the up ones. So when I would see bonds on your exam that would come like this, I didn't really know what to do with that because I'm like, it's neither axial nor equatorial, and it kind of looks like it's pointing up, but then you would have another one pointing up right next to it. And so then I'd be like, what is this? I don't know. It's not following the conventional standard. So what I used to do on my exams was I would actually draw this out. And then on my answer, I would like pick the ones I was picking You know, I'd be like, okay, this is exactly what they need to look like. Yes. I stopped in the top right corner because of what we're going to learn today about axial and equatorial. It's just easier for me. So I just always started the upright corner, but it does not matter. If you started like 1, 3, because let's see, it was 1, 3. The answer on the exam was 1, 3, and they both need to be pointing the same direction. So like if you were 1, 3 here and here, and they were both, they both needed to be equatorial, and they both needed to be pointing down. So if you did that anywhere, that was fine. But it started to get dicey when people would do like 1, 2, or they would do 1 axial, 1 equatorial. But it was like 1, 3, 1 axial, 1 equatorial, and they were both pointing up. And I was like, that's not possible. So there was just a few things that I was like, okay, we need to work on the conventional standard of like where up and down goes. Yes.
I'm sure you said this, and I probably just missed it, but how do you know the axial and equatorial? Like, it was both equatorial and yeah. How do you know that?
Yeah, so I do, there's a few different ways. So you could draw this, and then you could, so the question gave you the name, and in the name, I believe you had fluorine here, and it was R, and then you had tert butyl here, and it was S, I think. So 1, 2, 3, your hydrogen's already pointing back, so I just have to connect these, so that's R. Your hydrogen's already pointing back, so we don't flip it. This is the right way to calculate it. And then 1, 2, 3, your hydrogen's already pointing back, so that's S. So these are both wedges. We don't have to flip anything. This is the right convention. So once I get it in the flat structure, for me, that makes it a lot easier to convert because I know that both of these are pointing in the same direction. It could be up or down. It doesn't matter, but they have to be pointing in the same direction. Now, I typically start in the top right corner, so I would be looking, ignore that gray mark. That gray mark's not helpful. That is an example of what not to do. I would be looking at 1, 3. So here's what I've arbitrarily decided as 1, and here's what I've arbitrarily decided as 3. And I know they both need to be pointing in the same direction. So they'll either both be orange and up or green and down. Green and down puts them both in the equatorial position, and that's more stable. So that's the one I'm picking. So that's how I decide that these are both equatorial. Does that answer your question? Or do you mean, how do you know that this line is equatorial?
I just definitely need to work on it, but I just didn't know how you pick whether one was equatorial or not.
Yeah, so I look at this. The other way I do, and I'm pretty sure I also have a video in my tutorials playlist about this, is I'll just draw all the wedges because I know they alternate axial and equatorial. So like all these wedges alternate axial equatorial, so I'll just pick somewhere axial equatorial, axial equatorial, axial equatorial, and then I'm like 1, 3, so they're both axial, but they could also both be equatorial, right? They just need to both be the same. And then I go from there. Or if it's 1, 3 trans, I know that one of them has to be equatorial and one of them has to be axial. So I also will do this. So I go through usually the flat structure first because it's easier for me to visualize, but you can make a system that works for you. I had a student who was like, well, the flat structure is not real, so I'm never going to visualize it. And I was like, okay, do you? That's fine. But I don't know how to help you because I always go this way. So go find somebody on the internet who does it like you and then get your answers from them because I cannot go just through the chair. I've gotten better at going just through the chair. That was a few years ago. But okay. Any other questions? Okay, so work on this because it matters. It also matters for class today, as you will see. And I do encourage you, I call it topical review. So all these are like the things students ask questions about over and over. I would just like do a quick, they're usually less than 20 minutes review of like, you know, how to do that thing. So acid-base reactions, I think I have 3. People ask a lot of questions about chirality and meso compounds, so I have a bunch of stuff on that. Cyclohexane and chair, there's one just about how to draw it, and then there's one about how I convert, that would probably answer your question, Abby, between cis, trans, and axial equatorial. even what curved arrows are for and how to use them consistently if you're struggling with them. So you can come here and just creep on these and see if there's anything that helps you. And if there's not, if the question you have isn't answered here, you can email me and I'll ask you another one, or I'll make you a new one. Maybe not right away, but I will make it for you. Okay. Any other questions before we get started? Okay, what did we learn yesterday? You all are wrestling for your notes now. There's like panic in the air. What did we learn yesterday? We learned about elimination reactions, and what did we learn about them? I don't like that. Why is it doing that? Look, I told it to clone. What did you say? They compete with substitution reactions. That's right. They compete with substitution reactions. Tell me more about what they do. What are they? Not just you, anyone. They deal with beta hydrogens. That is excellent. I'm going to draw things up on the board while we talk. I don't know why I thought I could do this without drawing. They deal with beta hydrogens. And what is a beta hydrogen? It's a hydrogen that's what? It's more, I would say more accurately, that's close. I can kind of see what you mean there, but I would just tweak it a little and say it's the hydrogens that are off of a beta carbon. So we'll pick a carbon of interest at random. That's alpha, and then we have beta, and then gamma, and then delta. So our hydrogens in elimination reactions are the ones on our beta carbon. That's the one we care about. So we learned about elimination reactions, and we learned that they compete with a substitution. And we learned that they use beta hydrogens. What are the two different types that we learned about? Actually, what happens to this beta hydrogen? It gets got. It doesn't just leave. Something gets it. So your nucleophile acts as what? It acts as a base. That's how the hydrogen gets got. And then these electrons get left behind here and the leaving group leaves, right? And what does that make in the end? Makes a double bond. Which type of reaction, which type of elimination reaction have I drawn here based only on these arrows? E1 or E2? Who put up if you think it's 1, put up a 1. Put up if you think it's a 2. Why? Someone who chose a camp. A lot of you are like, I abstain, I plead the fifth. Someone who chose a camp, why do you think it's that? Why do you think it's E1 or E2? Well, there's a nucleophile involved in both of them, but I think you're on the right track.
All in one step.
I drew it all in one step. There we go. So all in one step is an E2 reaction. And what's the rate law of an E2 reaction? I saw somebody put up 2 fingers. Yeah, rate equals the nucleophile and the substrate, same as an SN2 reaction. So because the nucleophile comes here, the double bond is formed and the leaving group leaves all at once, that makes it an E2. What happens in an E1 reaction? If the same thing was an E1 reaction, what would happen? These are my beta hydrogens on my beta carbon. This is my alpha carbon. What's the difference? What happens in an E1 reaction? The leaving group just leaves. How does the leaving group leave? What is it stabilized by? What? Sometimes a carbocation left behind is stabilized by resonance. That's true. But also something in the Erlenmeyer flask that helps facilitate the reaction. this solvent has intermolecular forces that help to stabilize the leaving group and the positive charge that's left behind, right? So that's why it just leaves. It doesn't just leave. It leaves because it's kind of aided in leaving. And then what happens next? We still have our nucleophile here. What's the next step of an E1 reaction? Wow, that was really hard to say. The nucleophile takes a hydrogen. Hydrogen still gets got. And it makes an alkene again. So the end product of these would actually be the same. It's not always the same between E1 and E2, and we'll talk about that today. But ultimately, they're both forming an alkene. And they do both compete with their relative substitution. So E2 does compete with SN2, and E1 really competes with SN1. Why does E1 really compete with SN1? Can anyone think about that? Why might that happen? Why do those two really compete? The first step is the same. The leaving group leaves and a carbocation gets left behind. So if that's the thing we're waiting on to happen, then it's like, well, what's preferential? The hydrogen getting taken or the nucleophile attacking? We'll talk about how to make one preferential over the other today. Okay, so we learned this today, that E2 has the same rate law as an SN2. Yesterday we learned that, sorry, and it happens all in one step. E1 has the same rate law as an SN1, and it happens in two step, and the first step is the same, and so they're competing. What else did we learn? Nothing. Yes. What are the two different rules? Thank you. Zaitsev's rule and Hoffman rule. I'm going to spell Zaitsev wrong because they get spelled differently all the time, probably. Zaitsev versus Hoffman, and which one is which? What are they? What do they mean? Zaitsev is a smaller nucleophile. And so the alkene it makes, if there's two different options, say the leaving group was in the middle, you could take either hydrogen and you would get two different possible outcomes. It will take the more from the more substituted side. So the alkene will be more substituted. And we also learned yesterday that a more substituted alkene is also more stable. And sometimes Zaitsev is spelled like this. So all these start with S. Zaitsev gives you, it comes with a smaller nucleophile and it ends up with the more substituted and more stable alkene. Now, what about Hoffman? What is the Hoffman rule? Bulkier gives the less substituted, just the opposite in every way. Less substituted and less stable alkene is the outcome. I should have said more stable. More stable. Okay, great. So we learned that there's two different types of elimination reactions, and sometimes there's only one option. Like in this one, if I'd taken the hydrogen from either side, it would have given me the same alkene, but sometimes your leaving group is asymmetrical. And to decide if this hydrogen or this hydrogen is going to be taken, we look at the bulky or narrowness, the largeness or the smallness of the nucleophile. So the one internal is a smaller one. It ends up with a more substituted alkene, which we also learned about the stability of alkenes. And then if it's large, bulky, like a terbutyl or maybe even isopropyl, it'll go to this outside. Okay. What else did we learn? I don't know that I can think of anything else. I think that was the last thing. I wanted to do substitution of alkenes, but you jumped ahead, so we got both in one. Do you remember what those substitutions are called? Mono, di, tri, and tetra. Tetra substituted is more stable. Only di substituted is capable of cis-trans isomerism. And we're going to talk about what to do and how to tell the difference between things that aren't capable of cis-trans isomerism today. Okay, great. Now also remember, so right here on these 2 pages, I made notes about everything that we covered yesterday. This is, again, a good study technique for you. when you leave this class, you can make a one-page note of like, what is everything I learned? And then you can review it in the morning. And then you're interrupting your forgetting process over and over, and you're stabilizing those pathways in your brain. And I didn't need anything. I didn't look at notes. I just asked you guys questions to pull out of your brain. So highly recommend this as a study technique, and also how simplified down it is so that it's not, you know, tons of notes to look over. You've condensed the major concepts into just 2 little pages. Okay. I found out last night I can grade your uploaded stuff on my phone, and I was like, this is so much easier because it's smaller and I can just like swipe through. And I feel like that's the same thing with this. It's like, it's just smaller, it's more manageable. I can just like look at this and get everything I need very quickly. Anyway, okay, so today we're going to do our deep dives into E2 and E1. For E2, we're going to talk about what favors it. We're going to talk about the stereochemistry, not necessarily of the product, because we've already talked about that, which one is the more stable one that it would more likely form. We're going to talk about the stereochemistry of the reaction, and then we're going to talk about the names of these reactions. Then we're going to do a deep dive into E1. There's not as much going on in E1 initially. But after we finish these 2 things, then we're going to do what I like to call odds and ends, and then E1 gets a little bit more complicated. Sorry. Okay, so the E2 reaction, what favors it is just like SN2, E2 is favored by a strong nucleophile. So in the same way that an E1 and an SN1, the leaving group leaves, so you need a nucleophile that'll just like sit back and wait for something to happen before it can act. In an E2 and an SN2, there's no sitting back and waiting. The nucleophile is pushing the other thing out. In this case, it takes the hydrogen and then the electrons that leaves behind pushes the other thing out. But in either case, strong nucleophiles are going to be the ones that favor 2 reactions. So both SN2 and E2, where the nucleophile is involved, the nucleophile has to be strong to be involved. Okay, so this is especially favored. E2 is especially favored when paired with a tertiary leaving group. Why do you think E2 with a strong nucleophile and a tertiary leaving group is favored? Yeah, Michael? It does have to do with the area, but I am not going to take that response fully. But I'm glad you answered. What happens if you put a strong nucleophile with a primary leaving group? It can easily get to the carbon that the leaving group is attached to, so it's going to very easily do a substitution reaction. But remember, I threw up the primary, secondary, and tertiary on the board and was like, tertiary doesn't go through a substitution reaction with a strong nucleophile. Why doesn't tertiary go through a substitution reaction with a strong nucleophile? It's sterically hindered. There's that little picture that I like where the nucleophile tries to get at the tertiary and it bounces right off. So I actually agree with what Michael said to a degree, is that it's just easier. There's more options for the E2 to take a hydrogen from the tertiary. The reason there's more options for it to take a hydrogen from the tertiary is because there's so many hydrogens, which makes it sterically hindered, which means that the substitution reaction can't go. So there's almost no competition between an E2 and an SN2 if you have a tertiary leaving group. If you have a tertiary leaving group, SN2 can't really go, but you still have a strong nucleophile, so E2 is the next best option. So you have a strong nucleophile, the 2 reactions will be favored. If it's primary, it'll be more substitution, but if it's tertiary, it'll be more towards the elimination side. And then all elimination reactions are favored by heat. And what I mean by heat is like above 25. it's like a sliding scale. 25 is room temperature. Usually around 25, there will be a little bit, 25 degrees Celsius, that is. Around 25 Celsius, there will be a little bit of your elimination, but substitution will mostly be favored unless there's another mitigating factor like a tertiary leaving group. As your heat increases, you're putting more energy into your reaction vessel. So more energy is able to let this elimination reaction happen, which takes more steps and is less energetically favored. So you need more energy to get your elimination reaction. So it's not like you hit a temperature and then it switches over to elimination. It's more like it's a gradient. As we increase our temperature, we have a higher and higher percentage of elimination reaction. And then if you get to like 100 degrees and you're boiling, you're likely going to have primarily elimination and almost no substitution. Okay, and then also bulkier nucleophiles, for the same reason that tertiary leaving groups favor elimination, bulkier nucleophiles also favor elimination. So if you have a tert butoxide, which is the carbon with 3 carbons around it, tert butyl group, with an oxygen, O- on it, that is a big, bulky, quintessential nucleophile. That is going to favor, even though it's strong, it'll favor E2 over SN2. You don't usually see substitution with really bulky nucleophiles because they have a hard time getting into that substitution. When they do elimination, do you think those big, bulky nucleophiles give Hoffman or Zeithoff product? Hoffman, because they're bigger, not smaller, which is more stable, which is more Zeithoff. Okay. So let's talk about the stereochemistry of an SN2 reaction, or of an E2 reaction. So we talked a little bit about which alkene product would be more favored, but what we haven't talked about yet, I keep closing the visualizer for some reason. What we haven't talked about yet is actually to do an elimination reaction, everything has to be in the same plane. So what I mean by that is, we learned about the 3D shape of molecules, right? And all these are in the plane of the page, and then your wedges and dashes are going into and out of the page. Betrayed by my own visualizer. Okay. So we learned that these, come on, bro. There. Okay, we learned that all these straight lines are in the plane of the page, and these are coming out and going into the page, right? Okay, and then we learned in Newman projections that you could draw them like this. And these two are the ones in the plane of the page, and these two are your wedges and dashes, and then you can start to rotate them and get different configurations, right? Well, the reason I made you learn that is not just to learn how to visualize molecules, although I do think that's really important to do as a chemist, but also sometimes reactions need to be in a specific conformation in order for the reaction to work. So for elimination reactions, the leaving group and the hydrogen that's getting taken have to be in the same plane for E2 specifically, because E1 goes by a different mechanism. So our leaving group and our hydrogen have to be in the same plane. So that means we have a nucleophile that's coming to take our hydrogen, this goes here and this goes here, that would work. But if we had this same molecule and the leaving group was on our wedge over here, it would have to rotate before the E2 reaction would be able to take place. So you have to have your leaving group and your hydrogen anti to one another. So it is very, very helpful to be able to draw Newman projections quickly and easily if you're trying to determine if an elimination reaction can happen. So I'm going to give an example. I'll do it right down here. They have to be anti because they have to be in the same plane. So, you know, technically this wedge and this wedge are also in the same plane. And that's easy to visualize in a Newman projection, but it's hard to visualize in this 3D sawhorse structure. So I tend to go into the Newman projection, unless there's two hydrogens and then one of them can always be there, right? But if you have a CH3 here, this is also CH3, and a hydrogen here. And then you have your leaving group here, and a hydrogen there. You need to make sure that your leaving group and your hydrogen can get opposite to each other for this reaction to take place. So in this case, we could just draw our Newman projection. So we have this CH3, let's see. We're looking at it this way, the CH3 is coming towards us, so that would be on the right side. The hydrogen will be on the left side. And this is also CH3. And then your back carbon, the leaving group is coming towards me, so the leaving group would be over here. And this this one's in the planet page, and this hydrogen's here. So your leaving group, oh no, this is CH3. Do I have that right? Leaving group, hydrogen, CH3. Yeah. So your leaving group is anti to a hydrogen already. Great. So what that means is when your double bond forms, these two methyls are going to be on the same side of each other, and then you'll have a hydrogen and a methyl on the bottom. And this helps you know if you're going to get like a cis-trans conformation or which side your bonds are going to end up. So we need to know the configuration of the molecule in order to be able to predict what the outcome of the reaction is going to be. Now, if you have a chair conformation, this is called, you can ignore that one, that was a mess up. This is called being, I think it's anti-coplanar is what this is called technically. I just say they just need to be in the same plane. They need to be anti each other in the same plane. But we want coaxial is what we call it, for them to be in the same plane in a six-membered ring. So in a six-membered ring, for one thing to be pointing up and one thing to be pointing down and them to be perfectly anti to each other, they both have to be in the axial position. So this is why I always start up here. You guys asked me why I always start up here, is because if I always start here, it's very easy to see if this hydrogen is axial and in the same plane or not. So if I have this structure, so in this case, I'll have a bromine and that's pointing up, and then I have a CH3 that's also pointing up. The elimination reaction could happen on either side. You could end up with a double bond here. There's also two hydrogens here, so one of them has to be axial at any point. So you could also end up with, sorry, I forgot your CH3 group. You could also end up with a double bond over here. How could I favor this double bond over that double bond? Small what? Who said that? This small nucleophile does what? So which one cites this rule?
Smaller.
This one, yeah, the top one's the more substituted. So you would use a smaller nucleophile here, maybe something like an O minus, and you'd use a bigger nucleophile to get this one, maybe something like a tert butyl group. Don't worry, we're not rushing through this. Yes. They both have to be axial. It's called coaxial. So that means they have to be able to get into the configuration where both of them are axial. If you have a tert butyl group trying to go axial, that doesn't work. So if you have a tert butyl group, it can sometimes be locked into the equatorial position, right? We talked about that. So you also have to pay attention to that. Can the molecule even go into that configuration? Okay. I know you guys are like, what? So don't worry, I'll explain it again. So in an E2 reaction, the 5 atoms involved, so that means the nucleophile, the hydrogen, these 2 carbons, and the leaving group, all have to be in the same plane. So around a single bond in the Newman projection, we call that like a rotatable single bond. We call that anti-coplanar. So that's like the anti and the eclipsed. If they're anti and in the same plane, then we're good. So in the Newman projection, when it's staggered and your leaving group and your hydrogen are anti to each other, that elimination reaction can form. If it's in a ring, you have to do what's called anti-periplanar. It's also sometimes called anti-coplanar, but basically they both have to be in the axial position. So you can see in this chair conformation, there's a hydrogen axial here, but there's not a hydrogen axial on this side. So you cannot get two elimination products from this. You can only get one elimination product from this. So the stereochemistry dictates how reactions can work. So that's part of why I made you learn all that crap. Is so that you could use that to help predict the outcome of your molecule. The molecule that outcomes as your reaction. This is also just, we haven't had a chance to talk about this yet, but when a halogen is your leaving group, this reaction is often called dehydrohalogenation because you're losing a halide and a hydrogen. Hydrogen, halogen, halide, dehydrohalogenation. Yes.
For the last part, are they both?
I will accept it if you call them both anti-coplanar. I think anti-coplanar is technically for a bond that can rotate freely, like in a Newman projection, and anti-periplanar or coaxial is technically for the ring. But don't worry about it too much. So this is telling you the name, and this is the last thing I want you to learn before we get to do practice problems. Oh man, I forgot dehydrohalogenation. Here, I'll go to this practice problem for you, and then we can go back to that one. Okay, so I want you to do these practice problems right now. Stop what you're doing and consider whether or not you have two different possible outcomes for the reaction. And if so, just start with the ring on the left. And if so, then are they in the same plane and will the reaction actually happen? So I would start by converting, we know it's an E2 because there's a strong nucleophile and heat. So go ahead and start by converting this into a chair conformation to see if there are axial hydrogens next to your axial bromine.
Then we'll go back to more about dehydrogenation. This is the no. Oh, that's what I thought. Oh,
Okay, so interestingly, the thing that it seems like people are having the most problem with is converting from the thing to the chair. So good thing I showed you those videos and good thing we're working on this. Okay. So axial and equatorial are not the same thing as wedge and dash, right? So if we have, I'm going to draw both of my options for how I tell the difference again. So this is our basic ring. And if you're having a hard time getting your chair correctly, I start with 2 parallel lines and I connect them up and then 2 parallel lines and connect them down. Now I'm lazier and I do like this. And it never looks as good. See how much cuter this one is than this? Anyway. So this is your basic ring shape. Make sure that that looks right. And then I'm going to draw all my, let's do all my dashes. And all my dashes are going to be in orange. So axial, equatorial, axial, equatorial, axial, equatorial. Now I'm going to draw all my, wait, which one did I just say? These are all wedges. They're all coming towards us. They're pointing up. And then I'm going to do all the ones that point down. And then if this one's axial, this one has to be equatorial, right? So equatorial, axial, equatorial, axial, equatorial, axial. Okay. Now I'm going to draw it flat. And I'm going to draw all my wedges in orange. And these alternate, axial, equatorial, axial, equatorial. We only really need to be able to look at 2 though, because the structure we have is, it was a bromine wedge and a CH3 dash. Is that correct? Okay. Bromine and CH3. So one of these is pointing up and one of these is pointing down. So I just get to pick which one is which. So I know that I care about if they're axial or not. They want my leaving group and my hydrogen need to be coaxial. So I'm going to pick that my bromine starts right here and is axial. And that is why I always start in that corner, since you guys asked. So that's also why I put the one at the top as axial, is because that's just easy for me to kind of have those conventions. That's not like not everyone does that. That's just what I tend to do. So if this one's axial, we've picked it up here. Now we need to pick a down one next door. So here's a down one on the adjacent carbon. So carbon 1, carbon 2. This one's up, this one's down. So CH3 points directly down. Or if we look at it here, the CH3, if this is a wedge equatorial, the dash has to be axial. So you can pick either way that makes sense to you for how to convert from cis-trans to wedge dash. And if you need practice, go check out those videos. I noticed that on your exam, and then I also noticed it again when I was walking around. So if you're having a hard time with this, I would check it out. Okay, so that's how you get from, that's just your basic how you get from the chair to the, from the ring to the chair. Now we have to tell if we have coaxial hydrogens, right? This one's easy. There's only hydrogen, so one of them's always going to be coaxial. So there's definitely going to be a product where a double bond forms here. No question asked. But on the other side, is there a hydrogen pointing down? No, because the methyl's pointing down. The hydrogen is pointing up. The hydrogen is a wedge. So there's not a coaxial hydrogen here. So this elimination product can't happen. Only this hydrogen can result. So if you initially look at this, you might think, oh, there's a hydrogen here and there's a hydrogen here, and either one of these could be taken. So my possible products could be this or this. But when you investigate further, you can see that there's not a hydrogen here that can be taken because that hydrogen is not in the axial position. So this is not a possible structure that can be made. So no matter how bulky or how narrow your nucleophile is, you cannot get the more substituted product because stereochemistry does not allow for that to happen. Does that make sense? Okay. Now, in the Newman projection one, you don't have that same issue. You can rotate into it being always in a hydrogen opposite to the chlorine, but it will affect the outcome of if you have cis or trans. So actually, I want to change this practice problem. So don't do that one. Sorry for those of you who've already started. I'm going to make it a little bit different. Let's do bromine here. There's a hydrogen here. I'm drawing these out for my own thought processes. And then I'm going to make this side an ethyl. We'll make this a wedge. And the hydrogen in dash. Okay. So draw your Newman projection. And then rotate bromine and hydrogen on the beta carbon to be in the same position. Now over here we have 3 hydrogens, so one of these is always coaxial, so this is going to be one of our possible products. Surely, no question, this will still be a product over here. But we want to know if the elimination happens in here, it could be this, or it could be this. So we need to figure that out. So there's 3 possible products as a result of this elimination. So start by doing this. We're only looking at this, the beta hydrogen here being taken. We don't care about this one because we know there's always one that's coplanar to that one. So start by drawing your Newman and rotate your bromine and hydrogen on the beta carbon to be opposite of each other. Yeah. That's an ethyl. It's an ethyl coming towards you. You always Okay, I'm gonna do 2 Newman projections, depending on which one you drew, just so you can see it. I'll start by going from this side. The CH3 is coming straight down. The ethyl group is coming towards me, so it would be on the right. And the hydrogen is going into the plane of the page. And then on the back carbon, the bromine's coming towards me, so it would also be on the right. The hydrogen would be on the left. And the CH3 group is going straight up into the page. So you can see in this Newman projection, the bromine and the hydrogen are already opposite of each other. Now I'm going to do it looking from this direction because I think it's possible that people did it from both angles so that you can see if your Newman projection is right. So if I'm looking at it from this way, my bromine coming towards me is actually going to be on the left. And my hydrogen will be on the right. And then on the back, my ethyl coming towards me will also be on the left. My hydrogen will be on the right, and my CH3 is going straight down. So either way you drew it, you shouldn't have to rotate because the bromine and the hydrogen should already be opposite of each other. So if you don't have your Newman projections down, it's going to be harder to have this reaction work for you. So now I'm going to have my nucleophile come and take my hydrogen. A double bond will form right here. It's kind of weird to draw that arrow because it's between the front and the back carbon. And then my leaving group will leave. So the double bond forms right here in the middle. So the double bond has a CH3 on the top, an ethyl on the side over here, a hydrogen over here, and a methyl over here. So this is our, let's see, we have our CH3 and an ethyl on the same side. Ethyl CH3, ethyl CH3. So this is our right answer. So that's the beauty of Newman projections in elimination reaction. You have to be able to tell if it's anticoplanar. You need to be able to line up the bromine and the hydrogen, then you do your elimination. And then luckily, if you just cross these two out, this is where your double bond is right here. You have a CH3 and an ethyl on top and a hydrogen and another CH3 on the bottom. So this can help you if you're kind of trying to tell if it's going to be more of a cis conformation or more of a trans conformation. There's a specific nomenclature for that, but we won't do that just yet. Okay. So we're almost at a little break time, but before we do that, I do want to talk about dehydrohalogenation, and then we'll take like the 5-ish minute break, and then we'll do some random odds and ends. Okay. So dehydrohalogenation is technically the name of an elimination reaction when you lose a hydrogen and a halogen. So basically the one you've been doing over and over when your leaving group is a halogen, that's called a dehydrohalogenation. Just a special name for losing a halogen and a hydrogen. It's called dehydrohalogenation. I don't think it's that important that you know that name, but some people refer to it as that, so I wanted you to be aware of it. Sometimes elimination reactions, not just dehydrohalogenations, but any elimination reaction can also be used to make alkynes. So if you have an NH2-, for example, this is a really good nucleophile that is often used to make alkynes. And if you have two leaving groups, your reaction can go twice. So we talked about how substitution reactions can't happen on an sp2 hybridized, but elimination reactions can. So there's your first elimination reaction. You've seen this before. The nucleophile takes your hydrogen, the double bond is formed, and the leaving group leaves, and then you get a double bond, but you still have a leaving group and a hydrogen. So then your nucleophile, you have to have excess of this, will attack again and kick out your bromine, and you get a carbon-carbon triple bond. So not only do elimination reactions make alkenes, but they can sometimes make alkynes. Typically, NH2 is one of the only nucleophiles used to do this because it's very nucleophilic. Do you think this is an SN2, or do you think this is an E2 or an E1? Oh, it says, dang. It's an E2, but you could have told that just because it's a strong nucleophile and because the arrows are all at once. So here's an example of a dehydrohalogenation that makes a carbon-carbon triple bond. Sometimes, if it is a carbon-carbon triple bond at the end, this is known as a terminal carbon-carbon triple bond. So if the carbon-carbon triple bond that it makes is at the end of a chain, and that's still in the presence of NH2, which is really, really nucleophilic, what's the pKa of this hydrogen? Who said it? What did you say? It's 25. So that's pretty acidic compared to this when NH3 is 38. I have no idea what NH2 is, but I assume it's somewhere like way down low, like, or way huge, way down on the list, like probably 50 or 60. Very, very, very basic. Really wants to get that proton. So after your two elimination reactions have happened, actually an acid-base reaction can happen to deprotonate this hydrogen and leave behind a lone pair. And then sometimes this will be added to something with the leaving group, and then now this is your nucleophile. Crazy. So you can use a combination of elimination and acid-base reactions to make a carbon be a nucleophile. That's just a little tidbit. Okay, so we have finished all of the basics about E2 and E1. We didn't. The only thing, there's no special stereochemistry for an E1, but the only thing that really favors it over the SN1 is heat, except when paired with the primary, because it's not primary carbocations don't like to be formed. It is also favored by bulkier nucleophiles, and it is in really high competition between SN1 and E1, so that's really hard to tell. Okay, so we have covered all the basics of this reaction, of these reactions. There are some odds and ends that we need to clean up that we haven't finished yet. It's only about like 15 more slides, I think. And then if we have time at the end, we'll do more practice problems. But everything we've done so far today is eligible to be on your exam. So be sure to do practice problems like these. Okay, let's take a quick break and then we'll reconvene. Let's reconvene at 12:14, or wait, 16, 12:16. 5 minutes from now. Hi.
Is our final cumulative?
Yeah. It sure is. Well, think about this question. If it wasn't cumulative, this chapter, like in this chapter so far, we've done acid-base reactions, chemical confirmation, unit reaction, curved arrows. We talked about the shapes of the molecules. All of this chapter is already cumulative. So even if I said no, everything you're doing is cumulative. So it being cumulative actually makes your life a little bit easier, because there will be some questions that are like, name this. And you're like, oh, that's pretty easy. And then there'll be some questions that are like, use all. So it's like a little bit actually easier for it to be cumulative, because you'll have questions that are like, what's the shape of this molecule? And you're like, oh, I think about that all the time now. So already it's easier.
Will there be like a bigger focus from like the last chapters? That we have every time we talk about it?
Since we won't have a test on chapter 8, there might be a little bit more of a bigger focus on that.
Because I'm like the one that probably here early. Yeah. So
I think they have a quiz that week.
so
No, the last week that we're learning in material.
Yeah.
So you'll have a quiz that will cover our chapter 8. So next week is the last time we're learning new material, hopefully. So we finished chapter 7 today, and then we do chapter 8 a little bit on Monday, and on Tuesday, on Wednesday, I have a chapter 8 quiz. And then I might do some extra testing on chapter 8 in the final, but not a ton, because I do want to test you on everything. That's been done. You're taking it the Friday before, July 3rd. Then you'll want to watch the YouTube video about chapter 9.
okay, so we're ending it.
No, we're gonna do some chapter 10. too. So chapter 10 is really easy. So if you go to my YouTube, chapter 10 is like students are like, oh, that's amazing. And I happen to have short tutorials that basically tell you everything about those two chapters. I don't know if I'm doing any specific ones. I think in my mom's checking it out and just being. Yeah. Okay, so here. Okay, so if we go to this top 4 views. If you go to this top 4 views. Right here. How to understand NMRs, that's chapter 9. That I think I actually am gonna not teach chapter 9, and just tell people to watch this. Okay. And then how do the reactions work, that's chapter 9. So it's only 2 videos. But you need to do that. So do you think you like have those like the homework and stuff available before I take them? There's no chapter 9. So how? I think I talked about it. Okay. But it's like I don't even know how many there was at the final, but you just need to know stereochemistry. I think the best way to teach stereochemistry is to do it this way. I don't really think that so I'm getting over it. Some professors will do like a 1-day class on it and then it'll be on your exam. I don't think I put any on your final. I might have put like about and I'm just gonna go back and adjust it for what we covered. But chapter 10 definitely do practice. Okay. Oh yeah, so like that last. I just think, okay. For the last like week that I'm out there, like being the thing like to participation. So like really. But I won't really. And I think I want to try as much as we can to do review. If I do what I want to do with this video and like watch this video and that's my lecture on Mars and do some programming and then we'll do that, then we should have catch up day and we might just have to touch on so or I'll just take this weird week. So I think that we might just like finish up chapter 10 on Tuesday and then on Wednesday do review because I don't think we can catch up day. Well, or and then everything's pushed back. Is your final? Okay, so that's next Friday, right? 1 week from the chaos of it all.
I have a question.
Well, we're gonna start back on next one. Are you gonna ask after that? Okay, I just realized something in this conversation is that your final is in like 2 weeks, which is crazy. So just to give you an idea, we're actually pretty well on track, even though we stopped to do our debrief, because we are doing the quiz online this week. So that kind of gave us our time back. So my hope is that we finish chapter 7 today. I will have chapter 7 questions. You'll be responsible for everything we talked about today on your exam. I might do slightly less intense ones and then have a little bit more intense ones come back around for your quiz the following week. But that will be our last exam. Exam 3 is the last exam. So this exam that covers chapters 6 and 7 is your last exam. And then we'll have a quiz on Wednesday next week, and that will be your last quiz. And I'm hoping to be mostly done with chapter 8 by the time we get to that quiz. I think we'll maybe have to run over a little bit, but we'll be mostly done with chapter 8. And then we're going to go into chapter 10, which students usually really like, actually. It's very straightforward. Chapter 10 is radical reactions. And I think we might spill chapter 10 a little bit over into Monday, but I'm hoping to use the majority of, well, actually it's not Monday that week. That week's 4th of July. So we're pushing everything a week back or a day back. So that week we start the class on Tuesday. So we might have to finish chapter 10 on Tuesday, but I'm hoping to use most of Tuesday, Wednesday, and Thursday to do review for your exam, which is on Friday. Our exam's on a Friday because it's a holiday that week, so they push the whole class back. So your exam's on a Friday. Yes. Same time, same place. You'll have 2 hours to do your final, and it'll be twice as it'll be more multiple choice, but no free response. You're welcome. There might be a little bit of a heavier emphasis on the material we haven't covered yet, but it'll pretty much be evenly distributed with everything, but a little bit more of chapter 8 and especially 10, because we won't have even taken a quiz over 10 yet. Yes. Okay, so what I think I want to do for chapter 9 is spectroscopy, and it's valuable for you to learn if you're a chem major, which I think we have 1 chem major in this room, 2 chem majors in this room. So it's valuable for you to learn spectroscopy if you're a chem major. It's also valuable for you to have some resources on spectroscopy because you have to do an ochem project on spectroscopy. And depending on who your ochem 2 teacher is, they might want you to know some about chapter 9, which is spectroscopy. But I would rather you learn more about the way that electrons move. So I think what I'm actually going to have you do is I have a 20-minute video on how NMRs work. And I will probably just have you watch that video instead of us taking class time to do it. And then let you do just a few practice problems along with that video. And that will probably be the extent that we cover it, just because I do think that spectroscopy is one of those things that you don't understand until you've used it a lot. So like I learned spectroscopy theoretically in my NMR class, so I knew the very foundations, which is what I will teach you in the video. But then I didn't really get it until I took an ochem class where I got to do an NMR. Like I got to actually go into the room and put the sample in and it spit it back out and I had to interpret it. And so I really think that that's one of the better places where you can focus on that. And you will have a project in one of your labs where you have an NMR and you have to interpret it. But looking back at that video, I think will help you more than just trying to remember whatever we flew by in class. Yes. I don't remember. I already have the final written. I might have done it as bonus, but so I have like a basic final written and then I go back in and like, I'm going to change these few things to match what we covered in class this semester. So I think it will most likely either be as a bonus or as a, what's the product of this reaction? Here's an NMR that also will help you confirm that you predicted the right product, which is usually how it comes up on the ACS exam. I don't know how it comes up on the MCAT. One thing that's really interesting about NMR is it's the same technology as MRI. So we use it basically to look at how hydrogens are moving around in a carbon-carbon sample. And then on a much, much larger scale, MRI uses the same magnetic impulses to look at how molecules are moving around in your body to give you digital pictures, which is like crazy. So that's a cool thing about NMR, but I do think I would rather spend our class time on you understanding how electrons move and reviewing for your final and feeling more prepared. And then you just watch that video and use it when you have your interpretation stuff, maybe scrape up some bonus points. That's my thought about chapter 9. Dr. Bearhage does not cover chapter 9 in his class. So if you're taking summer 2 with him, you won't be responsible for that. Usually he makes it bonus on the final, the ACS final that he gives at the end of the semester. And I'll have the same number of questions on my final as you'll have on your ACS final. I'll tell you the details about that closer to time. And then he also, Dr. Dandekar does expect that you know NMR and expects that you know it really well. So depending on what your next step in ochem is, or if you're going back to your university, I know some people are just home for the summer, you'll want to do some digging and see if you need to learn more about NMR, but if you do, you can use that video as a jumping off point and always refer back to it instead of me throwing information at you in class and then us never talking about it again, which I don't think is valuable use of class. So be thinking about that. Now, the nice thing about summer is that you haven't had any time to forget what you've learned yet. So the other nice thing about final exams is for ochem 1 students typically do better on their final exam because there will be questions about hybridization, which you've had to think about over and over and over and over. And like, if you think back to the first week of class, we talked about how to draw carbon atoms. Now you know how to draw carbon atoms because we do it all the time. So there are questions on your final that you'll be like, oh, this is easy. Or you'll look back on your first test and you'll be like, why did I miss this? And it was because you're just learning it, but it feels a lot more natural now. So I encourage you in that way that usually you should work hard in preparing for it, but usually students do better. Okay. So let's clean up our random odds and ends from this chapter. So we're going to start with easy nomenclature. So cis-trans only works in some cases. Useful for 1,2 disubstituted alkenes if they're on 2 different carbons. That's what 1,2 means. We can do cis and trans, and then you can look at the hydrogens if they're on the same side or the opposite side. That's how we know if it's cis or trans. But if it's tri-substituted, it's a lot harder for us to tell that, right? So that's where easy nomenclature comes in. So this clearly is cis-trans. There's 2 hydrogens. We can see that the hydrogens are on opposite or the same sides. But if you have this substitution, we haven't learned a name for that yet. And if you swap out this CH3 with this bromine, it would be 2 different isomers, but we don't know how to write an IUPAC name that distinguishes between the 2 of them. So this is where easy nomenclature comes in. So lucky for you, it's the same rules as R and S to assign priority. So the first thing you'll do is assign priority to the groups around your double bond. And then you'll compare carbon 1 and carbon 2 to each other the same way we do in cis-trans. And if the 2 highest priorities are on the same side of the bond, just like if your 2 hydrogens are on the same side of the bond, then it will be, if it's opposite, sorry, we're starting with E. If it's opposite, it's integen, so E, because integen means opposite in German. I once had a German student who told me that I butchered that name, and I'm so sorry. She didn't really help me learn how to say it right, though. She's like, it's actually this. And I was like, oh, sorry. And then that was the end of it. And then Z configuration is for zusammen, which means together in German, so if they're on the same side. I think that this is so weird because E is like a letter that has all the lines on the same side, and Z is a letter that has things on the opposite side. So I want this to be switched, but it's not. So how I remember it is Z zame, like same and zame. I just switch S to Z at the beginning of the word same. So Z zame, if it's Z, they're on the same side. E opposite, they're both vowels. That's the only way I've ever been able to come up to remember it. So if you come up with a better name, that's fine. So let's do a practice problem on that. Well, I'll give you this example first, and then we'll do a practice problem. So on this carbon over here, I don't like the way they have it drawn, but on this carbon over here, chlorine is the higher priority, right? So on carbon 1, chlorine is the higher priority. On carbon 2, according to the Kahn-Ingold same rules as RNS, bromine is higher than carbon, right? So in this case, chlorine is the higher priority on carbon 1, bromine is the higher priority on carbon 2. So what do you think? Are these on the same side or opposite sides? Opposite. So that would be E. You can see it kind of outlined here. If the chlorine and bromine were on the same side of the double bonds, I'll use that same trick where I like cover up half the bond and see where the 2 highest priorities are. Then it would be Z. Okay, so that's why we have to do our Newman projection for our eliminations, because we have to tell if this is E or Z configuration, right? So going back to this one, I'm going to redraw it, but our 2 options were this. I think or this. These were our 2 options. This is an ethyl group. So let's assign priority. We'll start with this one, and we're going to look only at carbon 1. So both of these are carbons. so that's the same priority. But this carbon is attached to another carbon and 2 hydrogens, while this carbon is attached to 3 hydrogens. So this is priority 1 and this is priority 2. Do you agree with that? Okay, now the other side is easy because there's a carbon and a hydrogen. So this is priority 1 and this is priority 2. So these priorities are priorities are on the same side, so that is the configuration. The other option that we had was the priorities will stay the same. So 1, 2 is covering it up and seeing that 1 and 2 are on the same side. So if these are opposite, 1 and 1 on the opposite side, then that's E. Okay, so this is just a more specific version of cis-trans. So from this point forward, I only want you to use cis-trans if there are 2 hydrogens on opposite sides. That's the only time you ever get to use cis-trans. If it's anything else, you got to use E and Z. Okay. So for our Newman projections, when we get our elimination reaction, sometimes we might get cis-trans and sometimes we might get EZ. And you have to be able to tell on an E2 reaction, is this going to give me an E conformation or Z conformation? A cis or trans. You have to be able to tell. Okay. So that's one little bit of odd and end. The next odd and end is going to be a little bit more difficult, I think, for you. I don't know why that says stability of alkenes. I should say carbocations. So we've talked about how carbocations, the most stable is the most substituted, and then resonance like levels it up even from there. So most stable, substituted, least stable, least substituted. So primary and methyl carbocations don't really form unless there's an opportunity for them to undergo something called rearrangement. And rearrangement literally means that the carbocation will trade places with an adjacent hydrogen or methyl. Literally, an atom will shift over to fill in the carbocation to make it more stable, or a group of atoms will. You can only do this with hydrogen or methyl, and it plays out in both SN2 or SN1 and E1 reactions. So I have been lying to you. I've been giving you practice problems where rearrangement comes into play, and I haven't been making you think about it. That's because I wanted you to get the basics down first, and now I'm adding this in as a little bit of like decoration in your E1 reactions. So from now on, when you see a carbocation, I want a red flag to go up, red flag that says stop, check for rearrangement in your mind. So I'm going to give you an example of what this looks like. If we have a substitution or elimination SN1 reaction, so let's say we have this structure. And we have a weak nucleophile like ethanol. What's the first step if we have a weak nucleophile and any kind of good leaving group? The leaving group leaves, a carbocation is formed. So is this a primary, secondary, tertiary carbocation? What is it? It's a secondary carbocation. If this carbocation had a way to move over here, then what would it be? A tertiary carbocation. So what will literally happen is the electrons in this hydrogen will shift over to fill in that carbocation that's less stable and move the carbocation over. So now this carbon has 2 hydrogen atoms instead of just 1 that it started with. And that's because the overall molecule will benefit, even though it takes energy for the hydrogen to shift over. The overall molecule stabilizes enough that it's worth it to expend that energy for the stabilization to occur. However, you can't do that beyond a hydrogen or a methyl. Any larger groups can't migrate. So if we had this carbocation, one of these methyl groups could shift over. The carbon electrons will literally shift over And you'll end up with this structure. But if all these were ethyls and you had a carbocation next to it, nothing would change. That looks like a swastika. I'm sorry. I don't think Nazism is appropriate or good. Let's make them all turd beetles instead. Okay. So if you have this structure, then none of these groups can shift over because they're too large and bulky. If just one of these was a hydrogen, though, this carbocation would be moving over here so fast. So only methyls and hydrogens can do this. And I kind of just like think of it as a little switcheroo. They just like trade places. There's no convention of really how you're supposed to draw the electrons moving. So and like they just switch. Like this methyl group just trades places with the carbocation so that everyone's happier. It's just a little switcheroo. So anytime you have an E1 or an SN1 reaction, you already think, hey, the first thing that happens is the leaving group leaves. I want you to add a little to your little mechanism here that we made at the very beginning for your notes. I want you to add a little star that's like carbocation, look for rearrangement. Okay. Awesome. Yes, nothing bigger than that can ever move over. Okay, so here's another example of this. This is a secondary carbocation. If this methyl group moves over, so it's drawing the electrons from the bond between the carbon to move over, then this becomes a tertiary carbocation. So that's more stable. So methyl shift. A hydride shift is with the hydrogen with its electrons. They move over to go from a secondary carbocation to a tertiary carbocation. Okay, so I want you to do this practice problem. I give you the answers of what it will possibly make. Actually, no, I'm not going to give you this one yet. I lied. We'll come back to that. Okay, so let's talk about acid catalyzed dehydration, and then we'll come back to that practice problem. So the other odd and end that we need to clear up. So we've talked about easy nomenclatures, we've talked about rearrangement, and then we've talked about acid catalyzed dehydration. So acid catalyzed dehydration is a special type of elimination reaction. It encompasses E1s and E2s. If you have an alcohol, primary, secondary, or tertiary, is this a good leaving group or a bad leaving group? Does alcohol, have you seen alcohol be a leaving group yet? No. If you haven't seen it be a good leaving group, that's probably because it's not a good one. So alcohol is a bad leaving group, but sometimes you want to get rid of that alcohol. And if you add these alcohols with acid and heat, it will do an elimination reaction. And that's because the acid will undergo an acid-base reaction with the alcohol first to turn it into a good leaving group. It's easier for tertiary and secondary than primary. Tertiary and secondary go by an E1 and primary goes by an E2. This is just showing you which one's more easy to go by. So here's what happens. If you have these two, this ethyl, no, that's a propyl alcohol and acid, there's no good leaving group. So this can't be a substitution or elimination reaction. So if it's not a good leaving group, there's nothing that's going on here, then we have to ask ourselves what other kind of reaction could happen. Well, you've only learned about one other reaction so far, so your list is pretty short. The only other thing it could be is an acid-base reaction. And I see something that can act as a base, and I see an acid. So my guess is that these electrons are going to come and take that hydrogen, and your alcohol would become protonated. Now, if this leaves, what is it? What's the leaving group after it leaves here? It's water. Is water stable? Yes, so this is a good leaving group because after this leaves, it will just be water. So we've now converted this alcohol from a bad leaving group to a good leaving group with an acid-base reaction. So now you'll get an elimination reaction because now you have a good leaving group and you have a conjugate base. It might not be a super strong conjugate base, but it's strong enough for this to happen. So it will steal your proton, the electrons will fill in and your leaving group will leave and you have your double bond. Now let me ask you, why is this an E1 and not an E? Why is this an E2 and not an E1? Why won't this go by an E1 reaction? Why doesn't the leaving group leave first? After it gets protonated, why doesn't the leaving group leave first and leave a carbocation behind? Why does it go by E2 where it's all in one step instead of E1 where it's in two steps? That's definitely part of it. If water leaves, water's pretty stable. So once it leaves, it's happy, but is very energetically favored for the carbocation to be left behind? No. Also, this is a primary alcohol, so what kind of carbocation are you going to have? If a primary alcohol leaves and you have a carbocation left behind, is that a primary, secondary, or tertiary carbocation? If this group were to leave and you had a carbocation on this carbon, is that a primary, secondary, or tertiary carbocation? It's a primary carbocation because this carbon is only attached to one other carbon. Are primary carbocations favorable? No, you would much rather have a secondary or a tertiary carbocation. So this can't go as a primary alcohol unless there's a really good rearrangement that can take place, which there's not really. It won't go by an E1 reaction. This says SN2, but I should say E2, my bad. Okay, so secondary and tertiary alcohols go by E1. I don't know why that says this, and I'll fix it. So now I want you to do this practice problem. I want you to protonate your alcohol, let the leaving group leave, check for rearrangement, and then do your elimination, and then see what your final products are. Okay, we don't have very much class time yet, so I'm gonna work this with y'all. 1, 2, 3, 4. 1, 2, 3, 4. OH here. Okay. Wait. What was the structure? So H was secondary, not primary. Duh. Okay. So what's the first step that happens? If you add this to acid and heat. Is there a good leaving group here? No. So then what other kind of reaction could it possibly be? Acid base. So this is going to come take that proton. We'll say that H is bonded to an A, so that bond will break and leave us with A minus. Okay. So now what do we check for? Oh, wait. Sorry, I skipped a step. I'm too excited. OH2 plus. So now what do we check for after this is left or after this is protonated? What's the next thing that will happen in an E1 mechanism? This hasn't left yet. So there's not a carbocation. That's a protonated oxygen, not carbon. What's the first step in an E1 and an SN1 reaction? Leaving group leaves. So the leaving group leaves and you get a carbocation. Now, when you have a carbocation, I want your little red flag to go up that says, check for rearrangement. Anytime you see a carbocation, can this rearrange? Yes. Would it be a methyl shift or a hydride shift? It'll be a methyl shift because there's no hydrogens there. There's only 3 methyls. So a methyl will switcheroo. The carbocation ends up over here, and now we only have 1 methyl left behind on that side. Now, what's the next thing that you think will happen in an elimination reaction? Yes, Michael? Sorry. No, they're all the same. So what's the next thing in an elimination reaction? This favors elimination because there's heat, so it's not substitution, so it's not SN1, so there's not going to be any nucleophile coming in and bonding. So what happens instead? Hydrogen gets taken, hydrogen gets got. You can take it from over here. And these are the same, so it doesn't matter. Or, is there hydrogen there? Yeah, or from here. Which one do you think would be more favored? If you take that hydrogen from here, you get, if you take the hydrogen from here, you get, which one's more stable? This one's more stable, so how could we make sure we get the more stable one? Yeah? Who said it? How can we make sure we get the more substituted, more stable nucleophile? Someone said it. The smaller nucleophile gives us this more substituted, more stable site stuff. Okay. So that is acid catalyzed dehydration. It basically is an elimination reaction that shows you have to make your good leaving group first. Now let's talk about what is favored by what. Okay, if you have a strong nucleophile, does it favor SN1, E1, or SN2, E2? If you have a strong nucleophile, it favors 2s. Either SN2 or E2, and that's because in both of them, we're not waiting around for the leaving group to leave. We are attacking first, and the attack of the strong, very reactive, negatively charged nucleophile is the reason the reaction is happening. How can you tell if a nucleophile is strong or weak? Charge. In general, a nucleophile is more, if it's charged negatively, it's going to be a strong nucleophile. If it's neutral, in general, it will be weak. So if strong favors 2, I don't know why I put primary there. If strong favors 2s, E2s and SN2s, then weak favors 1. And we've seen that because a weak nucleophile sits back and waits for the leaving group to leave. Okay, now let's hone in on whether it favors SN2 or E2. So SN2 or E2. And then we'll also talk about SN1 or E1. So does SN2 happen more easily on primary, secondary, or tertiary leaving groups? Primary and secondary. I agree with that. I'm going to leave secondary down here because elimination can also happen with secondary. Okay, and then what about E2? What does it happen best with? Primary, secondary, or tertiary? It happens with tertiary. Secondary can actually kind of go either way. And that's more complicated. You have to look at the basicity. I probably won't give you any questions like that on your exam. You can usually just tell from if it's a strong nucleophile, it'll favor one or the other, and if there's heat. Okay, so then heat. What does heat favor? Substitution or elimination? So if there's heat, that will favor on that side. What about a bulky nucleophile versus a narrow nucleophile? Do narrows favor substitution or elimination? Substitution. So bulky favors elimination. Boom. You have already learned everything you need to know to be able to tell if it's an elimination or a substitution. That's why I didn't want you to worry about what was what until you learned all these characteristics. So if you have a reaction, first thing I want you to look at is the nucleophile. Is it strong or weak? If it's strong, then we're going to look at 2s. We're not going to worry about 1s. If we're looking at 2s, if you have a narrow nucleophile and a primary, that's definitely going to be an SN2. If you have a bulky nucleophile and a tertiary leaving group, that's definitely going to be E2. If you're sort of stuck in the middle, which doesn't happen very often, you can look at the basicity of the nucleophile, but usually if you have a secondary, if there's heat, it'll favor elimination. If there's no heat, it'll favor substitution in general. That's what I've seen. Okay, now ones are a lot harder because if you have a weak nucleophile, the first step that happens is the same, the carbocation leaves. So if you have a good carbocation, is that primary, secondary, or tertiary? Are carbocations more stable on primary, secondary, or tertiary? Tertiary. So both of the secondary is okay and tertiary is better. So both of these are equally favored, unfortunately, by secondary or tertiary. So the only things we can really look at to tell the difference between E1 and E1 and SN1 is heat and bulkiness. If your nucleophile is bulky, it's more willing to act as a base and abstract a proton. If it's narrow, it's more willing to act as a nucleophile and do a substitution. So you already know everything you need to know to be able to tell these four apart. If you use this flow chart, for the most part, you're gonna get answers right. So I want you to practice this weekend. I want you to go look at practice problems that make you tell if it's SN1, SN2, E1, or E2. And that's it, we're done. There's a chart that similarly goes over that if you want to look in your notes that I think is helpful, but I always use this mentality. Okay, see you Monday. I'll have office hours this weekend at some point.